Okay, welcome back to Corona Calculus. This is part 3. We're back to limits, sadly enough. But it's a little bit different this time. We'll be going with big limits and small limits. So we'll be covering kind of like the epsilon delta form of proof for limits going to infinity and 0. And then we'll cover a little bit of slope. Alright, let's get into it. So, well, let's start off with an example, right? You guys already know the epsilon delta form, I hope, of limit proofs. But say we wanted to prove that the limit as x approaches infinity of 1 over x equals to 0. So if we use epsilon delta, what's our delta? We don't really have a c here because we're going to infinity. So the key insight is that being close to infinity is the same as being really far from 0. It's like pretty big brain right there, right? So here's how we're gonna prove this. So if we say that the limit as x approaches infinity of 1 over x equals to 0, we're gonna say that this implies for any epsilon greater than 0, right? This is the same start as the epsilon delta proof, right? There exists a real number m, and m is like a really big number, all right, such that x is greater than m, all right? So what used to be x minus c is greater than delta. This is now x is greater than m. So there exists an big M such that x is greater than m, implying that 1 over x minus 0 is less than epsilon. Okay, so this part is the same as epsilon delta, and this part is the same. But now instead of having a really small delta, we have a really big m, and so that we have x greater than m now. So how do we do this as a proof? Well, let's see. I'm not really brushed up on this. Okay, so as with our old epsilon delta proofs, we have a pre-proof and an actual proof. Alright? So, let's see. This is what we want to show, right? As we did in our epsilon delta proofs, we start off what we want to show in our pre-proof, and then we can go backwards. So we want to show that there exists an m such that 1 over x minus 0 is less than epsilon. And of course we want to express epsilon in m now. So we have that 1 over x minus 0 is less than epsilon, or we can just say 1 over x is less than epsilon. So x is greater than 1 over epsilon. Maybe we can try that. So we have here that x is greater than 1 over epsilon, and we need to have that x is greater than m. So let m equal to 1 over epsilon. Remember, in our proofs here, we are trying to find an m based off of somebody giving an epsilon. It's like somebody telling you, here, I have an epsilon, can you find an m such that 1 over x minus 0 will be less than epsilon? Okay, so say we are given an epsilon, we will say to them that our m equals to 1 over epsilon, and therefore our x will be greater than 1 over epsilon, 1 over x will be less than epsilon, and therefore 1 over x minus 0 is less than epsilon. And by the definition of limits, we have proven that the limit as x approaches infinity of 1 over x equals to 0. End of proof. So that was like a rather simple epsilon and m proof. Let's see. We can. What should we do? We'll do one more example really quick. So example. Limit at x approaches 5 of 1 over x minus 5 cubed. Right? So you might go directly into an epsilon delta proof. Epsilon m proof, just like this. But you must see that if we go from the negative side of 5, this will be negative infinity. And if you go from the positive side of 5, you'll have infinity. So technically this limit does not exist. So for this proof, we'll say we'll go from the positive side, just to keep it nice. So for the pre-proof, we want to show that 1 over x minus 5 cubed will be greater than some m. Okay. So sorry, let's do our statement here. So therefore, for here, we're implying that for any epsilon greater than 0, there exists, oh boy, we're back to delta such that x minus c is less than delta, implying that, well, now we don't have an f of x. We can't do f of x minus infinity is less than epsilon. That's what we would have done with our old epsilon delta proofs. But this time we're going to say f of x minus a really big number is greater than 0. Okay, and our f of x here is 1 over x minus 5 cubed. So in our pre-proof, we start with what we want to show. Eventually we can do some math and show that x minus 5 is less than 1 over the cube root of m. Okay, then we can be like, oh, so our x minus c here is x minus 5, right? This is x minus 5. So back to our proof, we have a person giving us a delta, and we want to pick an m, or an m based off of that delta, such that f of x will be greater than m. So let delta equal to m cube root of m, sorry. So therefore, we are given this statement, this is already from the problem statement, that x minus 5 is less than the cube root of m, because of our first statement and then our transitive property here. And if we reverse this, we're going to get x minus 5, 1 over x minus 5 cubed will therefore be, wait, shoot, did I miss something up? This should be 1 over, sorry. So 1 over the cube root of m. And therefore 1 minus x minus 5 cubed will be greater than m. Simple proofs. We don't need to spend too much time on this. Okay. Last slide. So we're going to do a little bit of a slope here. Hopefully this video won't be running too long. So let's see. If we have the limit as x approaches 2 of x squared plus 3, and say we want to find, say we have a function x squared plus 3, and we want to find the slope of the tangent line of f of x at x equals to 2. Okay, so how do we do this? Well, we could say that we can approximate the slope, right? So slope equals to delta y over delta x, right? And our y just simply equals to f of x, or delta f of x, right? So let's see what we can do. If you are just stumbling, why not just start with the approximation as delta x approaches 0, right? So to find our slope, we would clearly have delta x on the bottom, and then we'll have something like f of x plus delta x minus f of x, right? This is what we're going for. So this equals to, if we plug it in, limit as delta x approaches 0 of delta x plus x squared plus 3 minus x squared plus 3 all over delta x. Okay? And if we expand this out, this equals to the limit as delta x approaches 0 of delta x squared plus 2 delta x times x plus x squared plus 3 minus x squared plus 3 all over delta x. And we can see that this cancels with that. And if we divide through, we have equals to the limit as delta x approaches 0 of delta x plus 2x. Now we can evaluate the limit. You don't want to have to do any proof for this. Clearly, as delta x approaches 0, this will just equal to 2x. Cool. So we have our little expression of our slope, and we can see that 2 times 2 equals to 4. So the slope of the tangent line to f of x at x equal to 2 should equal to 4. Now there should be an algebraic way you can do this, expressing your tangent line with a quadratic formula, but I'll leave that to you guys. Pretty cool.